Hi guys, this is Subhro sir from Calcutta. In the previous videos I taught you set theory preliminary portions. Today my target is to build a concept on some important properties of sets, partition of a set and Cartesian product of two sets. This is an important portion of set theory, so don't skip this video. Watch till the end and let's start. My first topic is to discuss some properties on union and intersection of sets. The first one is consistency property. The three relations B is a subset of A union B is equal to A, and A intersection B equal to B are mutually equivalent. That means one implies the other two. Now from this we can derive some other properties. They are A union phi equal to A intersection phi equal to phi, because phi is a subset of any other set. Also, the second property is A union U means the universal set U is always equal to U. A intersection U is equal to A, because A is a subset of universal set, because any sets are subset of universal set. Again, the third property is A union A is equal to A intersection A equal to A. That means it's called the idempotent property of a set. Remember it, it's called the idempotent property of a set. And the fourth one is A union A intersection B is equal to A, and A intersection A union B is equal to A. As A intersection B is a subset of A, it's obvious, and A is a subset of A union B, it's also an obvious case. And this property is called absorptive property. Absorptive property. The next property is commutative property. It means A union B equal to B union A, and A intersection B equal to B intersection A. Next property is associative property. It's equal to A union B union C. It means A union B union C. A intersection B intersection C is equal to nothing but A union A intersection B intersection C. And finally it's distributive property. It equal to A union B intersection C is equal to A union B intersection A union C. And finally A intersection B union C, it is equal to A intersection B union A intersection C. We can prove all these properties, and let's look at an example to prove these properties. Suppose we are proving the distributive property A union B intersection C equals to A union B intersection A union C. Then let's take an element X. Let X be an element in the set A union B intersection C. We have to first prove that this X belongs to this set. Then we can say this set is a subset of this set. The first set is a subset of second set, and then also we have to prove the contrapositivity that the second set is also a subset of the first set. That means first set is a subset of second set, and the second set is a subset of first set. Then these two sets are obviously equal. So first we have to prove that the first one is a subset of second one. So we have taken an element X in the first set, then X belongs to A union B intersection C. Now we know union means or and intersection means and. So X belongs to A union, that means or. X belongs to B intersection C. So X belongs to A or X belongs to B intersection means and X belongs to C. Now we can write X belongs to A or X belongs to B, and in the middle we can write and X belongs to A or X belongs to C. You know, or means union, so X belongs to A union B and X belongs to A union C, it's C. Now and means intersection, so we can write A union B intersection A union C. So the x is an element, was an element of the first set, and we have proved that x is also an element of the second set. So we can write that A union B intersection C is a subset of A union B intersection A union C. It's number 1. Now also we have to prove the second part. So contrapositively, let another element y is an element of the set A union B intersection A union C. Then y belongs to A union B intersection A union C. Now similarly, intersection means and, so y belongs to A union B and y belongs to A union C. Now you guys know that union means or, so y belongs to A or y belongs to B, and y belongs to A or y belongs to C. Now we can take a common, y belongs to A or, and in the bracket there is y belongs to B and y belongs to C. Now also y belongs to A or y belongs to, and means intersection, so it's B intersection C. Again or means union, you know this one. So y was an element of the second set. Now we have proved that y is an element of the first set. So it's quite obvious that A union B intersection A union C is a subset of A union B intersection C. It's number 2. Now combining 1 and 2, we can write that A union B intersection C is equal to A union B intersection A union C. So it was the distributive property of sets. Now in the distributive property there was another theorem. We can similarly prove that one. Also we can prove the other theorems. So try it yourself. Now we will discuss some properties of complement of a set. The first property is A union A complement is equal to the universal set U, and A intersection A complement is equal to the null set phi, because phi is a subset of any set. That means phi is a subset of A, and A is a subset of universal set, because all the sets are subset of the universal set. So obviously A is a subset of universal set. And the second property is A complement whole complement is equal to A, nothing but the set A itself, for any A subset of U, the universal set U. Next we are to proceed towards De Morgan's law. It's an important property of complement of a set. De Morgan's law says A union B whole complement is equal to A complement intersection B complement, and A intersection B whole complement is equal to A complement union B complement. Now we can prove all this by the previous process. Let's prove the first one. An arbitrary element X in the set A union B whole complement. Then we can say that X is not an element of A union B, because X is an element of A union B complement. Then X is not an element of A union B. Then we can say X is not an element of A and X is not an element of B. So X is not an element of A means X is an element of A complement, and X is not an element of B means X is an element of B complement. So now AND means intersection. We know it. We have done it previously. So X belongs to A complement intersection B complement. Now we have taken X as an element of A union B whole complement, and we have proven that X is an element of A complement intersection B complement. Therefore we can say that A union B whole complement is a subset of A complement intersection B complement. It's the first part. Now we have to prove the second part. let y be an arbitrary element of A complement intersection B complement, then y belongs to A complement intersection B complement. Now we know intersection means and, so y belongs to A complement and y belongs to B complement, and so y belongs to A complement means y does not belong to A, and y belongs to B complement means y does not belong to B. Now y does not belong to A and y does not belong to B means y does not belong to A union B. For the complement case, and means union and or means intersection. Remember it carefully. And so y does not belong to A union B means y belongs to A union B whole complement. So y was an element of A complement intersection B complement, and we have proven that y belongs to A union B whole complement. So we can say that A complement intersection B complement is a subset of A union B whole complement. It's number 2. Now combining 1 and 2, we can say A union B whole complement is equal to A complement intersection B complement. So this was the required proof. So the first part of De Morgan's law we have proven, and the second part is remaining for you. Do it yourself. Now we will learn the concept of family of sets or the set of sets. We have defined the set as a collection of its distinct elements or objects. If the elements are the sets themselves, then we will have a family of sets or the set of sets. Suppose the collection of all the subsets of a non-empty set S is a subset of sets. This set is said to be the power set. We have learned this one previously, and this set is denoted by P of S. Clearly, if S obtains n distinct elements, then P of S contains 2 to the power n elements, 2 to the power n subsets. Let I be a finite set 1 to up to n, and F be the family of n sets A1, A2, An. Then F will be expressed as F is equal to A alpha such that alpha belongs to I, where I is called the index set of the family F. If the index set is equal to the set of all natural numbers n, then it can be expressed as An such that n belongs to natural number. Let I be an arbitrary set and A alpha such that alpha belongs to I, where I is the index set, be a family of the subsets of the universal set U. Then we can say that the union of the family of subsets can be expressed as union alpha belongs to index set I, A alpha is equal to X belongs to U, the universal set U, such that X belongs to A alpha for at least one alpha belongs to I. Remember this one, this is for at least one alpha belongs to I. And the intersection of the family of subsets can be denoted as, expressed as intersection alpha belongs to interset I, A alpha is equal to X belongs to universal set U, such that X belongs to A alpha, where alpha for all alpha belongs to I. This sign means for all. So remember this one, this notation means for all. This is an universal notation and used everywhere in mathematics. In particular, we can say that for a finite family of subsets F is equal to A1, A2, A3 up to infinity, and we can say that the first property, union of I equal to 1 to n, AI is equal to X such that X belongs to AI for at least one I. Intersection of I equal to 1 to n, AI is equal to X such that X belongs to AI for all I, or it can be written as for each I. The third property is union of I equal to 1 to n AI whole complement is equal to intersection of I equal to 1 to n AI complement, and intersection of I equal to 1 to n AI whole complement is equal to union of I equal to 1 to n AI complement. Now we can proceed towards some examples. The first one says for each n belongs to natural number, let I n is equal to the closed interval 0, 1 by n. Then we can say that I1 is a subset of is a superset of I2 and is a superset of I3 and so on. And intersection of n belongs to natural number in is equal to nothing but the singleton set 0. And the second example is for each n belongs to natural number, if in equal to open interval 0, 1 by n, then I1 is a superset of I2, is a superset of I3 and so on, and n belongs to natural number in equal to nothing but the null set phi. Now we will proceed towards the partition of sets. Partition of set says let S be a non-empty set, a family of non-empty subsets S alpha such that alpha belongs to intersect I is said to form a partition of S if the first condition is union of alpha belongs to I, S alpha is equal to A, and the second condition is S alpha intersection S beta be equal to the null set phi for each alpha beta belongs to the intersect I, and obviously alpha not equals to beta. The condition 2 says that the family of subsets S alpha such that alpha belongs to I is pairwise disjoint. In particular, a family of non-empty subsets S1, S2, Sn up to Sn of the non-empty set S is said to form a partition of the set S if S1 union S2 union up to Sn is equal to the set S itself, and Si intersection Sj is equal to phi for each Ij belongs to the intersect I and I not equals to j. Let's look at an example of a partition of a set. Suppose C0, C1, C2 and C3 are the four subsets of the set of all integers Z, where C0 is equal to it's C2 and C3. Where C0 is equal to 4n such that n belongs to the set of all integers, then obviously when n equal to 0 the value is 0, when n equal to 1 then the value is plus minus 4, when n equal to 2 the value is 8, when n equal to minus 2 then the value is minus 8, so it's plus minus 8. For C1 it's 4n plus 1 such that n belongs to the set of all integers, then it's equal to 1, 1 plus minus 4, 1 plus minus 8 and so on. And the C2 is 4n plus 2 such that n belongs to Z, then it's equal to 2, 2 plus minus 4, 2 plus minus 8 and so on. And C3 is equal to 4n plus 3 where n belongs to set of all integers, then it's equal to 3, 3 plus minus 4, 3, 3 plus minus 8 and so on. Then each of C0, C1, C2 and C3 are the non-empty subsets of the set of all integers, and we can say that C0 union C1 union C2 and C union C3 is equal to nothing but the set Z itself, that means the set of all integers itself, and Ci intersection Cj is equal to the null set where I not equals to j and Ij is equal to index 1, 2, 3, 4. Hence we can say that these two satisfies the property of the partition of a set. So the given subsets C0, C1, C2 and C3 form a partition of this set of all integers Z. Now our target is to build a concept on Cartesian product of a set. Let A and B be two non-empty sets, then the Cartesian product of A and B is denoted by A cross B and is defined by A cross B is equal to the ordered pair AB such that A belongs to the set A and B belongs to the set B. In elaborately we can say that let A1, A2, An be finite collection of non-empty sets, then the Cartesian product of the collection of the sets denoted by A1 cross A2 cross An which is equal to x1 the ordered pair x1 x2 xn such that xi belongs to ai, that means x1 belongs to a1, x2 belongs to a2, x3 belongs to a3 and so on, and finally xn belongs to an. In particular, if a1 is equal to a2 is equal to a3 is equal to up to an, then the Cartesian product is denoted by a to the power n. It is actually the set of all ordered n tuples that means x1, x2, xn such that xi belongs to A. Let's look at an example to clarify this Cartesian product. We have taken a set A which is equal to 1, 2, 3 and a set B which is equal to 4, 5. Then A cross B is equal to 1, 4, 1, 5, 1, 4 and 1, 5, 2, 4, 2, 5, 3, 4, 3, 5. And the set B cross A is 4, 1, 4, 2, 4, 3, these 3, and finally 5, 1, 5, 2, 5, 3, these 3. So actually we can say that it is quite obvious that the number of the Cartesian product of the sets A and B is nothing but the product of the numbers of elements of A and B. That means the cardinal number of A cross B or the cardinal number of B cross A is equal to the cardinal number of A into cardinal number of B or the cardinal number of B into the cardinal number of A. Now we have already read what the cardinal number is. If you guys don't know, so you have to watch the previous video on set. I'll mention the link in the description box. Please go through it. So guys, set theory is over today. In the next video I'll start relations and mapping, and I'll try to elaborately describe those chapters, as some people find difficulties in the main concept and differences between two chapters. So keep watching my videos and get updates by subscribing my channel. Also don't forget to like, share this video and to support my channel. So thank you.